Hello, pre-calculus class. In this video, we're going to take a look at how to find the equations of polynomial functions using Desmos, and also take a look at how to decide what type of function, like what degree polynomial function would fit your table the best, fit the data the best. So we have an example here where your x values are going up sequentially, starting at 1 and then just increasing by 1 each time, but your y values are kind of jumping all over the place. Start at 7.5, go up a little bit and go down a bit more, and then start to increase really rapidly. So let's use Desmos to create this table and get an idea of what we're working with. So we'll go over to Desmos, and to create a table in Desmos, you hit the little plus feature here and click table, and we'll create a little table with x1 and y1 values. My x's went from 1 through 8, so we'll type 1 there, hit enter, type 2, and a nice trick to Desmos is that after you hit enter then, it will just keep populating all the rest of these, so we wanted to go through 8. My y values now I have to actually plug in with 7.5, 8, 6.5, 6, 9.5, 20, 40.5, and 74. Right. Drag on the y-axis to kind of compress this up a little bit if you want. X-axis moves it around. I kind of want to see most of the things going on there, but there you go. This is my data. Looking at this, I can kind of see it might be increasing here at first, then decreasing, and then increasing again. So again, from the last video, I know this has an increasing branch, a decreasing branch, and then finally an increasing branch again. So 3 distinct branches means that this is probably a cubic function. So that's a good way to kind of give yourself a little bit of a guess as to what type of function might best fit this data. In here too, there's another way to really nail it down. If you're trying to find, and this only works for kind of the theoretical data. This is not great for real world applications, but if you had an exact cubic function, an exact third degree function, it would end up looking kind of like this if you made a list of what we call the differences, right? So the differences are just that. They're how far apart, what's the difference between each item in this list. Okay, this only works if the x values are going up in order, right? That has to be evenly spaced x values here. It doesn't have to be sequential. It doesn't have to be 1, 2, 3, 4. It could be 1, 3, 5, 7, but it has to be increasing in a sequential order, right? But then here, if I would look at what's the difference in those y values, right, and I make a list of those, and so for this one I made a column of what we call the first differences, or just the differences of the data, right? So from 7.5 to 8, it's going up by 1/2, right? From 8 to 6.5, it's going down -1/2. And so I want to make sure I make that distinction, right? When you're making a list of these differences, don't just do 8 minus 7.5 and then 8 minus 6.5. You have to decide, am I going up, increasing a positive difference, or am I going down, decreasing a negative difference? If I keep making this, I get a list of all of these first differences. Right? That doesn't still tell me a whole lot, right? It's not very organized here. But if I continue on now, if I make a list of the second differences, which is the difference of the first differences, right? How far apart are the first differences here? So from 1/2 to -1/2, that's going down 2, right? The difference between those 2 points is -2. It's going down 2. From -1/2 to -1.5 to -1/2, it's going up 1. Then I add 4, then 7, then 10, then 13, and this is starting to look a little more familiar to you. This is just a nice linear pattern where it's increasing by 3 every time. And if I lay that out explicitly, say, hey, here are the differences of the second differences, which we call the third differences, right? I can see that it's +3 every time. So I know that this initial data, right, the table over here, that data has constant third differences. And maybe you talked about this in Algebra 1 with quadratics that have constant second differences. A cubic function will have constant third differences, right? And a fourth degree function would have constant fourth differences, and a fifth degree function constant fifth differences. That is a theorem of polynomial functions. A polynomial of degree n will have constant nth differences, or an nth degree polynomial will have constant nth differences. So since this has constant third differences, I know that it is a cubic function, or third degree function, which would look like this. You can write with the subscripts: a sub 3 times x cubed, a sub 2 x squared, a sub 1 x, and a 0. Or, and this is probably the way that you'll see more often, starting with that alphabetical a first, and then just going alphabetical: ax cubed, bx squared, cx, and d. And so to find this equation, we want to go to Desmos, right? So if I'm in here and I've made my graph, right, to use Desmos to find this, they have a nice feature where you can find the equation of basically anything, any type of function that you want. And so I have my general equation that ax cubed plus bx squared plus cx plus d. We're going to use that with this data. So to do this, you can't type just y equals, right, ax cubed plus bx squared. It'll, right, if I do that here, it will be asking me for sliders, right? It's trying to create its own equation and where you put in the data. But if I actually use the data that they have here, right, the y1 is approximately, you have to use that little like tilde symbol. For me, it's the shift and then like the key right next to the 1, right above the tab button. And I can do ax1. Right. To get those subscripts, again, you just have to type a 1 after it. There's nothing fancy. You don't have to hit anything. It's just x1. Right, so ax1 cubed plus bx1 squared plus cx1 plus d. And it will give you this best fitting thing here. Again, to get the exponents in Desmos, you can just hit like the shift 6, the caret key, puts it up there, or you can use the keyboard if you need to, right? This little a to the b power will give you that option to make things up there. But key things, right? You need to use that tilde symbol instead of the equal sign, and you need to make sure that you're using the subscripts. If you don't use the subscripts here, it will not work. It will ask you for what you think the a, b, c, and d values are, which doesn't work very well. And if you're trying to find it here. So now you have these a, b, and c, and d values. You know that it should be that for the cubic function y equals 1/2 x cubed minus 4x squared plus 9x plus 2. And you can have that going through all of your points there. This thing, this r squared here, tells you what the fit is. So we knew that from the data, this was exactly a cubic function because it had exact constant third differences here. And so this will tell me, right, yes, it is 100% on. There's no error in this. If you were to plot the error bars here, it's just 0 all the time. These 10 to the negative 15ths. That's right. It's 1.77, but there's 15 zeros in front of that one. It's like 0.0000, 15 zeros until we get to there. There's no error between any of these points and the actual function itself. So let's get rid of those, right? If I want to actually do some stuff with this function now, if I wanted to say find, right, what would f of 9 be, I can't do it on here very well. I can't type in like y1 of 9 or anything like that, but I can type in a new function using those parameters, the 1/2, -4, 9, and 2. You can use the numbers, right? I can type in y equals 0.5 x cubed minus 4x squared plus 9x plus 2, and it will go right on top. You actually can just use the letters themselves. Also, I can just write in f of x equals ax cubed plus bx squared plus cx plus d. And this will work because we've already defined what our a, b, c, and d values are up here. So then if I wanted to find, say, like what's the next number in here, I can find what is f of 9 going to be, and it would predict, right, this is supposed to be 123.5. I'm going to look at one more example, one that doesn't have exact graphs. So there's, this is example 2 in the book, page 682. They ask a bunch of questions about this, but I'm just going to kind of go through how I could find the equation of this. And so this one, if I were to look at the data, it would not have any constant differences of any kind. It's a little bit more random, more real world data, but I can still kind of tell some of the features of this, right? It has a low point there, goes up, comes back down, and then goes back up. And so if I were to think of like what's a graph, it might look like an increasing branch, decreasing, and then increasing again, which would again be a cubic. So I can find the line of best fit doing the same thing that we did before. You remember my subscripts, it's y1 is approximately that tilde ax1 cubed plus bx1 squared plus cx1 plus d. Right? And so if I use this, it will give me, right, here's my best fitting data through these points, right? It's not perfect, right? Like this is real world data. This one is maybe a little bit higher than the data would predict, and these two are a little bit lower than the equation would predict. But that would give me my equation of best fit. Again, this little value here, this r squared, this is telling me that, right, there's some error, but it's still pretty good, right? This, like, the closer to 1 you are, the more perfect the data is. So this is saying it's a pretty good approximation, this cubic function here. And yeah, there's going to be some error between the actual data points and the function itself, because it's not a perfect cubic, but it's pretty close. Right? I can also make one that looks even closer than this. Right? And so I went in here, and here I just made it be a 7th degree polynomial function, right? One that this thing has an r squared of exactly 1. Right? So if I turn this on, here is what that 7th degree function would look like, going through pretty much each of these points completely perfectly. But if I look at my original initial data here, right, this stuff that's going on over here, like there's no prediction, there's no reason why that would even be happening, right? Like it should be going up, then down, then up again, and there's nothing in the data that says, oh yeah, then it also goes back down before it goes back up, right? So that 7th degree function, while the best fit technically, right, I probably wouldn't want to use it because it's assuming some other information about this data that might not necessarily be true. And right, that if I change even just like one other thing, it would change the thing wildly. It would change this graph wildly depending on what that was. So there's that. I can also take a look, right? If I take something else away, here's a 6th degree function that still, again, has a much better r squared value than that. But it goes off, decreases really rapidly at the end here, which there's nothing in this data to indicate that it turns around immediately at 9. It's probably not a great representation of this, right? And I could just kind of keep taking things away, right? A 5th degree function fits it pretty good, even better than that, but it assumes a bunch of stuff over here, and this negative, this drop at the end. A 4th degree function, the same thing, still better. So you can get closer, technically, r squared values, things that fit the data better, but I want to stick with what the initial data actually kind of shows, right? This increase, decrease, and then increase again. So this should be enough information to let you interact with some of the questions in the book, answer some of those. There's some interesting questions that kind of have you explore this a little bit, that they have you actually finding the equations algebraically. There is a way to do that we have not talked about yet. So anytime it ever asks that, just go back to Desmos, right? Find the equation like this and answer the questions that they have for you there.